All right, everyone, we had a little bit of homework last night. Worksheet number 2 on impulse. We'll give you some answers to that, and we'll go over any questions that we need to go over. Question number 1, I got 80.0 kilograms meters per second. What's another set of units we could have used for the momentum or for the impulse in question number 1 besides kilograms meters per second? Newton seconds, good. Either one of those would work. Question number 2, I got 1.20 times 10 to the 4 Newton seconds or kilograms meters per second. Question number 3, I got 1.46 times 10 to the 4 Newton seconds or kilograms meters per second. 4, I got 2.67 times 10 to the 3 newtons. 5, I got negative 8.33 times 10 to the 3 newtons, or essentially we're saying we have a backward force of 8.33 times 10 to the 3. 6, I got 675 newtons. Now that could have been a negative value depending upon which way you defined as positive and which way you defined as negative. I defined, let's see here, I defined the positive direction as away from the soccer player and the negative direction is toward the soccer player, so therefore I got a positive value for the force. Had you defined it opposite to that, you would have got a negative 675, but the magnitude would have been exactly the same. Number 7, I got negative 21.0 Newton seconds. Number 8, I got 60.0, positive 60.0 newtons. Number 9, I got a change in velocity in number 9 of 5.0 meters per second. Any questions from worksheet number 2 that we need to go over here today? Number 9, yeah. Any others besides number 9? Going once, going twice? Okay, number 9 it is. Number 9 is force versus time graph. Don't even know what we're being asked right now, but what are the first 3 words that come to my mind when I see that force versus time graph? What is it? Good, area equals impulse. So we know that we're ultimately going to calculate the area of this graph. Whether we're actually trying to find the impulse or whether we're trying to find something else, we're going to need the impulse to get whatever we're looking for. Again, whether that's the final answer or not. Let's check our units here on the axes. We got newtons and we got seconds, so we're all good there. We don't have to do any kind of conversion there. Let's get the area of this. The area is equal to the impulse, and of course, in this case, that's equal to 1/2 base times height because it's a triangle. So we're going to say 1/2 of 10 seconds times the height of, looks like 4 newtons. That's going to give me an area of 20, and the units will be Newton seconds. Don't get mixed up with this and think back to, like whenever you learned area in grade 6 or whatever it was, and say, oh, it's 20 meters squared. It's 20 meters squared if your 2 axes are meters and meters. But when we've got newtons and seconds, then of course the area of that is going to be newtons times seconds, which is impulse. Now, if we're trying to find the change in velocity, we're going to set that impulse that we just found equal to mass times change in velocity. You're going to rearrange that to solve for delta V. It becomes delta P over m. Delta P is 20. The mass, we said in the question, was 4.00. We do the division there. 20 divided by 4 ends up being equal to 5.0. And the units, of course, for that are going to be the standard units of meters per second. Make sense? Now, understand that we've just solved for the change in velocity. Had this question given you an initial velocity, let's say it started off at an initial velocity of 8 meters per second, and it asked you not for the change, but it asked you for the final velocity. We would do the exact same thing to get the change in velocity of 5 meters per second. It just wouldn't be a final answer. The final answer would be 13 meters per second in that case, because we'd add the change in velocity to the initial velocity. Does that make sense? No other questions on that worksheet? All right, yesterday we talked about the law of conservation of momentum. We said that in an isolated system, the total momentum of the system will always remain constant. It always stays the same. You don't gain momentum, you don't lose momentum as long as we have this isolated system. Does anybody remember what the isolated system was? system in which neither energy nor mass come in or out. So you don't have any external sources of energy or drains for energy. You don't have any external sources or drains of mass. You don't have mass or energy coming in or out, which ultimately means, of course, if you don't have any energy coming in or out, then you don't have any external forces. So basically what we want, no external forces acting here, which gives us no energy coming in or out. And of course, it stands to reason that if you want to use the law of conservation of momentum, that you're not going to have any mass coming in or out of the system either. Now, we're going to use that, we said yesterday, when we analyze collisions, which are pretty self-explanatory. Two things hit each other, that's a collision. Whether they stick together, bounce apart, doesn't matter, and that's a collision. We're also going to use it, however, when we have what we call an explosion. An explosion could be literally a bomb blowing up. Okay, it could be literally anything exploding, but it could be something as simple as you standing on ice or a really slippery surface and throwing a rock. The rock goes forward, you go backward. We consider that to be an explosion because it's one object becoming two. You and the rock acting as one object, becoming two objects after the interaction takes place. So we use it whenever we have a collision or an explosion. Now, we also said yesterday that that doesn't preclude the possibility of us having an impulse. Right? We talked about impulse for the last few days. Impulse is the change in momentum. Okay, a lot of people will think at this point, if we say that momentum has to be conserved, momentum has to stay the same, that what we learned over the last few days must be wrong. You can't have a change in momentum. We can. Impulse can, there can be an impulse on individual objects within a system. There can't be an impulse on the system itself if we have an isolated system. So for example, we fire the gun. The example that we used in the video that we watched yesterday from Lethal Weapon. We fire the gun. The bullet goes one way, the gun goes the other way. What was the momentum of the bullet before the bullet was fired? What was its value before it was fired? 0. What was the momentum of the gun before it was fired? 0. The total momentum was 0. But afterwards, the bullet has momentum. So there was an impulse experienced by the bullet. The gun has momentum. There was an impulse experienced by the gun. But the total momentum stays the same. The momentum of the bullet changes, the momentum of the gun changes, but the total momentum stays the same as 0. By the way, how do we reconcile that? How do we say if both objects are moving, the gun and the bullet, how do we say that the total momentum is still 0? Bullet's got a momentum of 10, let's say, to the right. What does the gun have a momentum of? 10 to the left, right? 10 to the left. So 1 is positive 10, 1 is negative 10. What does positive 10 add up? Positive 10 combined with negative 10 add up to be? 0. Total momentum remains 0. One final question here. If the gun has 10 units of momentum and the bullet has 10 units of momentum, why isn't the gun just as lethal as the bullet itself? Because it has more mass. If it has more mass with the same momentum, then it's obviously going to be moving slower. Right? And that's the critical factor there, right? Is the gun isn't going back nearly as quickly as the bullet is. All right, the equation that we established yesterday to describe all this is Pi is equal to Pf. The total initial momentum, Pi, is equal to the total final momentum, Pf. Now, if we have two objects, we're going to say the total initial momentum will be m1 v1 initial plus m2 v2 initial. So the momentum of object 1 plus the momentum of object 2 equals the total initial momentum. We could change that around a little bit if we had to. If there was 3 or 4 objects, then we just add in a couple more terms. After the collision, we would say m1 v1f, m1 v1 final, plus m2 v2 final. So the total initial momentum of both objects combined equals the total final momentum of both objects combined. Now, again, the momentum of each individual object can easily change, but the total momentum of all the objects added together will always remain the same if we have this isolated system where we have no external forces acting. Let's take a look at an example here. This is 9.6 from page 477. It says, a wooden block attached to a glider has a combined mass of 0.200 kilograms. Both the block and the glider are at rest. We're going to say that's VI on a frictionless air track. A dart gun shoots a 0.012 kilogram dart into the block. The velocity of the block dart system after the collision is 0.78 meters per second. We're going to call that VF. What was the velocity of the dart just before it hit the block? You know what? Let's call the dart object number 1, and let's call the block object number 2. If that's the case, we're going to say that the block V2I is 0 meters per second. Because it says the block and the glider, right? The block and the glider that it's on are not moving. We're looking for the velocity of the dart just before it hit the block, so we're looking for V1I. That make sense? We've got V2I, the velocity of the block isn't moving. We're looking for V1I, the velocity of the dart, just before it hit the block. What's this 0.200 kilogram thing? Is that M1? Is that M2? Is that the mass of the block or the mass of the dart? Which one is it? A wooden block has a mass of 0.200 kilograms. That's going to be M2. Now it says the dart has a mass of 0.012 kilograms. So we're going to say that's going to be M1. What do you want to call this VF here? The velocity of the block dart system after the collision is 0.78 meters per second. You want to call that V1F or V2F? The velocity of the block after the collision or the velocity of the dart after the collision? It's both, isn't it? The dart and the block are one object now. The dart's stuck to the block. It tells me the velocity of the block-dart combination or system after the collision is 0.78. Let's just call it VF. If it was one or the other, we'd call it V1F or V2F, but it's not. It's both of them combined. Let's just call it VF. If you want to call it V12F to remind us that it's both of them combined, then go ahead and do that. I'm going to just choose to call it VF, though. All right. We're going to say PI is equal to PF. We know that the total momentum is going to stay the same. The momentum of each object will change, but the total momentum in the system is going to stay the same. The law of conservation of momentum. How many objects do we have before this collision takes place? We got a dart. We got a block. How many objects is that? 2. So let's have 2 terms. PI is made up of M1 V1 initial plus M2 V2 initial. The momentum of the dart before the collision takes place plus the momentum of the block before the collision takes place. How many objects do we have after the collision takes place? 1. The dart has stuck in the block. So we're going to say that the total final momentum is just going to be mvf. It's the combined mass times the combined velocity. 2 objects become 1. That's the collision. M1 is the mass of the dart, and we've established from our givens that that's 0.012 kilograms. V1I is what I'm looking for here, the velocity of the dart before the collision has taken place. M2 is the mass of the block. The mass of the block is 0.200 kilograms. What's V2I? What's the initial velocity of this block? The velocity of the block before the collision takes place. It's 0. So if we want to, we can just cross this term off. Because what's 0.200 kilograms times 0? 0. Now, if you want to write those variables in and do the calculation and show that calculation, that's fine. But if you want to take this little shortcut that we've just taken and just cross that term off because we know that one of the variables in that term is 0, then you can go ahead and do that as well. What's m here? It's probably the toughest part of this question. What's m? It's the combined mass. The block was 0.2 kilograms. The dart was 0.012. The combined mass is going to be 0.212 kilograms. And the final velocity is given to us in the question here as 0.78 meters per second. So now we've got a fairly straightforward mathematical problem now that we've set this up. So we get V1I is equal to 13.78. We're going to round that to how many digits? Let's go back to our givens here. 0.200 looks like 2 significant figures here and 2 significant figures here. So our final answer should be rounded to 2 digits, which would be 14 meters per second. So before the collision took place, the dart was moving at 14 meters per second. After it took place, the dart-block combination was moving at only 0.78 meters per second. Anybody explain to me why it slowed down so dramatically? Moving at 14 meters per second, it goes down all the way to 0.78 meters per second. If the momentum stays the same, the momentum of the dart is the same as the momentum of the dart-block combination after the collision. Why did the speed change so much? Cool? Because the mass is different. The mass is much greater. If the momentum is the same and the mass is a lot more, then the velocity has got to be a lot less. Right? Does the solution to that question make sense, everyone? Good. Good. I'll get you guys to work on a couple of questions here right now on page 477, please.